Good day everyone. Today we will be talking about solid geometry. We will be gonna discuss some theorems in solid geometry. So we already done with theorem 1 to 6. So we're gonna start with theorem number 7. To be able to explain the theorem number 7, we will gonna use this door. So as you can see, that this door has two lines here, which are parallel to each other, this one and this one. So we were gonna prove that two lines are parallel to each other through the plane, which they are both perpendicular. So and the converse of theorem number 7 that if one of the two parallel lines are perpendicular to the floor and the other also. So if this line here is parallel to the perpendicular to the floor, this line here is perpendicular to the floor, so therefore this one also is perpendicular to the floor because they are parallel, right? So and if you look at also that this floor is form a rectangle. So one of the characteristics of the rectangle is two pairs of parallel lines. Hi, we were done with theorem 7, so we were gonna proceed with theorem number 8. So to be able to explain the theorem number 8, we were gonna use this wall, this floor, and this line here. So we were gonna prove that this line here is parallel to the intersection of the floor and the wall. So we all know that the plane has infinite length, right? So this wall can be extended because it has infinite length. This wall also can be extended because this floor also can be extended because it has infinite length. So if you can see that they are intersecting at this point, at this line, the intersection is a straight line. So and since we have another line here which is perpendicular to the intersection. I'm sorry, I mean this parallel to each other, not perpendicular, right? So since that they are parallel, the intersection of the wall and the floor, and this one line here, which is lying in this wall, are parallel to their intersection. So since that they are parallel, we can say that this line is parallel also to this floor, the plane, because this line is also lying in the floor. And to explain theorem number 9, we have our ceiling as our plane, and we have our floor as our second plane, and we have also this pillar as our line. So you can see that this pillar, the ceiling and the floor, you can see that the ceiling and the floor is both perpendicular to the pillar. So therefore we can prove that they are parallel to each other. The ceiling and the floor are parallel to each other, right? So we can prove also that each one of the ceiling and the floor is perpendicular to the pillar. Therefore, the other also. If the ceiling is perpendicular to the pillar, therefore this floor also is perpendicular to the pillar, because we have proved that they are parallel to each other through this pillar. So we are now in drawing number 10. So we're gonna use the ceiling to be able to explain and explore also. So as you can see that this corner here, this one, and this one. So align, we all know that alignment is length, right? So this one here, our line can be extended. This other also can be extended. So therefore they are intersecting. So since they are intersecting, therefore they are determining this plane, this floor as our plane in drawing number 2. A plane can be determined by two intersecting lines. So given that these two intersecting lines are parallel to the ceiling, so therefore we can say that the floor and the ceiling are parallel also, because the two intersecting lines which are parallel to the ceiling is determining the floor as a plane. So therefore they are parallel, the ceiling and the floor are parallel to each other. So to prove current 10, we were gonna use the some part of this glass room. Come in. So to be able to prove the current 10, we were gonna use this corner here, this room. So we were gonna use this floor as our plane, and we were gonna use this corner as our point. So we were gonna prove that through that point there is only one plane can be drawn perpendicular to this floor or plane. So first, through that point we're gonna draw a line which is drawn perpendicular to the plane. This line here can be drawn perpendicular to the floor as our plane. Our next step, we will gonna draw two intersecting lines, which is their point of intersection is that point. So that line here is going to be considered as that line there. They are intersecting at that point, and through that two intersecting lines, which is when the section is that point, they are now determining plane, which is the ceiling. In drawing 2 intersecting planes can determine two intersecting lines can determine a plane. So they are now determining the ceiling, and showing like that plane is perpendicular to this line, and this plane also, the floor is perpendicular also to the line. So therefore they are perpendicular to the same plane. So we can say that they are parallel to each other, the ceiling and the floor. So we can prove that there is only one plane drawn perpendicular to the floor through that point. So we are now in theorem number 10. So to prove theorem number 10, we're gonna use this corner here as our first line, and that line there in the ceiling as our second line. To prove that, through that, as you can see, the two lines never meet, but they are not parallel. They are few lines. So to prove that through that line there, to prove that there is only one and only one plane can be parallel through that few lines. First thing, we will gonna draw another line which is intersecting this one few line here. So we are gonna draw a line here, this one in the corner as our line. This one. As you can see, they are intersecting, and we are determining this plane by showing two intersecting lines can determine a plane. And as you can see also that this line here is parallel to that line there. So therefore, through that line, through that one few line, and we have through this we drawn one line also, we prove that there is only one and only one plane can be drawn perpendicular to that few line there. To prove theorem number 13, we are gonna use some part of this study sheet. So first, we will gonna have our line here, this one, and this is gonna be our second line, this one, and we will gonna have a point, this one, which is not on the two non-parallel lines. So to prove that through this point there is only one plane can be drawn parallel to these two non-parallel lines. So first, we were gonna draw two lines which is parallel to both of these non-parallel lines, and that two lines is intersecting at this point. So this is gonna be our drawn line which is parallel to this line, and second one, this one, which is also parallel to this line here. So since that they are intersecting at this point, now through theorem 2, a plane can be determined by two intersecting lines. So they are now determining this plane. So therefore, we prove that there is only one plane can be drawn perpendicular to these two non-parallel lines. So that's theorem number 13. I'm sorry, that was parallel. That was parallel to these non-parallel lines. This plane is parallel to that two lines, which is non-parallel.
By the way, good day. I am Bacas. I'm going to discuss for you about the theorem 14 to 18 and what is a diagonal. That's all. So first of all, we're gonna discuss and I'm gonna explain to you theorem 14. So theorem 14. In theorem 14. To prove theorem 14, first of all, we have two lines here. So you can see that line there, and line here, and this line here, and this line here. As you can see, that both lines intersect each other. Therefore, they can make a plane. So as theorem 2 states that two intersecting lines make a plane. So therefore, both these lines here are now a plane, and this line here is also a plane because it has two intersecting lines. So therefore, this plane here and this plane here are parallel to each other. So they are parallel to each other. Then since they are parallel, then this angle here, this line here, and this line here are equal to each other. We are now done at Theorem 14, so let's move on to Theorem 15. So to prove Theorem 15, we have a great example here. So this is this building. So we have a plane. We need three planes to prove and two lines to prove Theorem 15. So the first plane is that blue roof there. First, and the second roof there is our second plane, and the third plane would be that third roof, and we have two lines there, which is the first pillar and the second pillar. And as you can see, the lines intersect all planes. So therefore, the straight lines there are perpendicular to each of the planes. So therefore, they are parallel to each other. Each of the planes are parallel to each other. So we all know that each floor has the same length with the first floor, and the second floor, and the third floor. So therefore, the lines there, the first pillar there, the lines there are proportionally, therefore they are proportionally equal to the planes, from the plane to the second plane and to the third plane. Dihedral. Do you know what is dihedral? No? So lucky for you, I'm here to teach you what is a dihedral. So a dihedral is a figure formed by two intersecting planes. So as an example, this is a plane here. Do you know what is a plane? Then this is another plane. As you can see, a dihedral, I can say this is a dihedral because they have the characteristics of a dihedral. So this is a plane here, and this is another plane here. That is a characteristic of a dihedral. And lastly, they have a common edge. That is the characteristics of a dihedral. So these two planes intersect each other, as you can see. So they form 90 degrees or angle something, maybe 45 or 30. So, as an example of dihedrals, dihedrals have three kinds of dihedrals. First is a dihedral which has half plane and a whole plane and whole plane. And last is a whole plane and a half plane, like this one. This is a whole plane and this half plane. Do you understand that? First of all, this pattern here is a cube figure. Theorem 16. To prove that Theorem
we have a diagram over here. I can say that this is a diagram because it has the characteristics of a diagram. The diagram has a plane, two planes. This is the first plane, second plane, and they go on edge. And we have this another diagram here. We have another diagram here. This is the first plane, and the second plane, and they go on edge. So therefore, this is a diagram. And I can say that to prove that there is this true, we all know that all sides of a cube has an equal size. So the angle form I diagonal here is same as this diagonal here. So therefore, there are equal to each other. That's all. Hi. And we're gonna prove theorem 17. So we have to prove the theorem 17. We have two planes. So first, this is our first plane here, and this floor our second line. This first plane here is the wall, and the second plane is the floor. And we have in the wall we have a point here, and that has a line through this point here, till here. So therefore, and we have another line that is on the floor, which is here that intersects at the floor line, at the wall line. So as you can see, this line here is perpendicular to this line for this plane of the wall, and the line from the wall, this line here is perpendicular to this line on the floor, or this line here is perpendicular to the plane 2. So therefore, both planes, the floor and the wall, are mutually perpendicular to each other. It's me again. So to prove theorem 18, we have three planes. So this is our first plane, second plane, and the third plane. So the first plane was the first wall, second wall, and the floor. Both planes 1 and 2, we're going to both extend this plane here and this plane up to there. And as you can see, this plane here, both planes here are perpendicular to the floor. And these both planes here have their line of intersection. As you can see, this is a line here, which both planes intersect. So therefore, this line of intersection of both planes here is perpendicular also to this floor.